Welcome back, everybody. Today we're looking at some of the basic force problems where we have a series of forces that are known to us or that we could figure out acting on some object. And we probably want to know about something to do with the motion of the object, or maybe we'd go the other direction, know something about the motion and some of the forces and have to figure out something about an additional force. A few basic steps that we're going to be taking on all of these problems. The first of which is going to be to draw a free body diagram. This would be that picture where we show our object as a dot, and then any forces that are acting on it will show as arrows pointing away from the dot. So, and then label those arrows. Maybe this is a pulling force, maybe we have gravity here, force of friction, something like that. And I guess to make this complete, I'll put in a normal force as well. So we'll draw out our free body diagram. That helps us figure out which forces in which directions are going to influence motion in those directions. The other piece to this is we're going to examine these forces from the standpoint of Newton's second law, which says that the acceleration vector for an object is equal to the net force vector, that's the vector sum of all the forces acting on the object, divided by that object's mass. So we could use that relationship to go between knowing things about the motion, some of the kinematic stuff that we've done, so knowing about velocity and position, time, those things. We can get to acceleration from there and then switch over to knowing something about forces and then use that information to solve for an answer about forces, or we could go the other direction, know about the forces and solve for acceleration and then get to the kinematic stuff. Where we go from here is going to vary on a problem-by-problem basis. What we really need to do is have an understanding of what different types of situations we might face. We might have a situation where forces are balanced, either in the x direction or in the y direction, or possibly in both directions. Whenever forces are balanced, this term here, the net force, is going to be equal to 0, and so that means acceleration is going to be equal to 0. If we have evidence that the object isn't accelerating in one dimension or the other, then we know that the forces in that dimension must balance out. So for example, if I'm pulling a box across the floor, that box may be accelerating horizontally, but unless I'm lifting it off the floor or it's falling through the floor, it's not accelerating in the vertical direction. So I could say then that all the vertical forces must balance each other. So let's take a look at a couple of different situations with these. We'll do some practice with these concepts so you get a sense for what types of relationships we're looking for. In this situation, we have two different forces that are acting on an object. The frictionless plane thing. We're not talking about an airplane, just a surface, a level surface without friction, so we don't have to consider that for our calculations here. Now, we don't actually have any frictionless planes, so this is just something we do in physics to simplify problems. We could have a situation where there's very, very little friction, and so it wouldn't make a whole lot of difference if we ignored the friction. We get a pretty good estimate without that. But we'll talk about how to handle friction later on as well. But for now, just these two forces, and we're asked about the displacement after 3 seconds. Displacement is one of those kinematics quantities. I'm given information about forces, so that tells me, all right, my basic process here is going to be to figure out what the overall force is, the net force, then use that to figure out what the acceleration is, and then once I have acceleration, I can go back to the kinematics equations from earlier on and figure out how far it's moved and in which direction. Since it starts from rest, the direction here is going to be the same direction as the overall force, the net force acting on this thing. But to begin with, I need to find that net force, and to do that, I'm going to begin with a free body diagram. Free body diagram always starts with a dot to represent our object. When we draw these out, we're only going to have one object shown. If you have multiple objects interacting, you need to have separate free body diagrams for each one. We have a force at 30 degrees north of east, so that'd be something like this. I'll say that north, east, south, and west to look like this. Oops. Okay, west, there we go. So I've got 30 degrees for this one, and that is 25 newtons. And then 60 degrees, and that one is 35 newtons. So you can imagine that our overall force is going to be somewhere in between those two. So let's go ahead and figure out what that would be. First step then, finding the net force. Now that we've got the diagram made up, is going to be to do the vector addition for this. So I'm going to break each of those vectors into their x and y pieces, and the x's and the y's, use those to combine into a single vector. I think it's useful in diagrams like this to separate the forces into their own diagrams, and on the AP exam they don't want you to use your free body diagram to break vectors into their components. That's something that only should be done on a separate diagram. So my separate diagram then, I'll have one for the 35 Newton force and one for the 25 Newton force. Now with each of these drawn separately, I can go through a little trig to figure out how far in the x direction they each go and how far in the y direction they each go. So for force 1, I can break that up like this. Here's my x component and my y component, F1x, F1y. Do the same thing for the blue, the second force. And we'll call that F2x and F2y. And then I can use trig to solve for each of those x and y components. So by using sine and cosine, I can get the x and the y pieces here. For the first force, we have 21.65 newtons using cosine. Then using sine, we get 12.5 newtons, and that's the y side, the opposite side. On the second force, we get 17.5 for the x part, 30.31 for the y part. Whenever I do these, I like to check at this point and make sure that I haven't forgotten a negative sign anywhere. So for my first force here, that's going up and to the right. So my x part is to the right, that's positive. My y part is up, that's positive. This one also is up and to the right. To the right is positive, up is positive. If I had any left or downward arrows, I'll treat those as a negative. And then I don't have to worry too much about how the math comes out. I don't have to think too much about direction because the negative sign is keeping track of that for me. Now I'll add the x's together, add the y's together, and make a new triangle for my overall force. Now with my components for x and y figured out by adding the individual components, I see that overall in the x direction we have a force that's a positive 39.15 newtons, so I'll draw that as a vector to the right. Oops, need to draw it, there we go. 39.15 newtons. And then in the y direction, 42.81 newtons, it's positive, so that'll be upward. Draw that starting where the first vector left off. That's how we show adding vectors, of course. 42.81 newtons. And then my overall force, let's try that again. My overall force here needs to point, there we go. That direction, this is my net force. And I do need to find the angle with that because that's a vector quantity. So to get the net force magnitude, we'll do Pythagorean theorem. For the angle, we'll do inverse tangent. At this point, I've solved for my net force. I know both the magnitude and the direction for that. So 58 newtons at 47.6 degrees. That'd be 47.6 degrees north of east. I'll just make myself a note about that for later. I don't need to worry about writing this out just yet because this isn't the answer that I was looking for. Instead, I'm looking for a displacement. Now that I know force, my net force, I can use Newton's second law, the equation that goes with that, to figure out the acceleration. And then once I have acceleration, I can use that to figure out the displacement. So a couple more steps still to come. The equation then is the acceleration vector equals the net force vector divided by the mass. The net force I've figured out is 58 newtons, and then the direction is at 47.6 degrees north of east. That's my direction. Divided by the mass was given to me up at the top of 5 kilograms. And so I have an acceleration vector then of 58 divided by 5, which is 11.6 meters per second squared at 47.6 degrees north of east. Next step then, I need to figure out what that translates to for displacement. So this is a kinematics question. So let's go ahead and get the information we know written down for that. So in this problem, we're looking for how far it ends up from its starting point. I decided just to call the starting point position of 0. We only have motion in one direction here. We don't have a projectile motion problem or anything like that right now. So I'm just going to say that whatever direction it's moving in, that's the 47.6 degrees north of east, we'll call that the x direction here. It starts from rest. We don't know what speed it's going to get at, but in that direction that I'm looking at, I know the acceleration is 11.6 meters per second squared, and I know how much time it's traveling for. I'm looking for the final position. So the equation that makes sense to solve for this one is the x equals x naught plus v naught t plus 1/2 at squared equation, where x naught is 0 and v naught is 0. So this is going to leave us with just x equals 1/2 at squared. So x is 1/2 11.6 meters per second squared times 3 seconds squared, which gives us of 52.2 meters. Now at the very end of this problem, I want to write out my answer as a sentence that relates back to the question. The question was, what's the displacement of this box after 3 seconds? So my answer, I will write that the displacement of the box is 52.2 meters at 47.6 degrees north of east. Remember, displacement is a vector quantity, so we do have to include that direction. All right, back to the overview here. We had the problem. We started out by drawing a free body diagram. We made new diagrams to break that vector up into its x and y pieces around here. We added the x's together and added the y's together to get our overall x and y components, which we then used to solve for the net force magnitude and direction. Once we had the net force, both the magnitude and the direction, we were able to calculate the acceleration and the direction that went with that. And once we had acceleration, we could take that back to the kinematics equations to figure out the displacement. That's all for this one. If you learned something on this, please be sure to like the video, ask questions in the comments section, and if you'd like to see more videos like this, go ahead and hit subscribe. Thank you.